Ever felt like you're just drowning in information? Especially when you're trying to get your head around something complex like organic chemistry mechanisms.
Oh, absolutely. You learn the basics, right? Additions, substitutions, eliminations.
Yeah, the standard stuff. But then sometimes molecules just seem to go off script. They like completely change shape, rearrange their entire skeletons, or even just break.
They do. It can seem kind of random at first
It
glance.
does. Like they have this secret life we weren't told about.
But what's really fascinating, this is the core of it, is that it's not random at all. There's a deep logic behind it, a kind of hidden elegance to how dynamic these molecules actually are.
And that hidden elegance, that logic, is exactly what we're aiming to unpack today. Welcome to the Deep Dive, your shortcut to being well-informed.
Yep. Today we're diving into Chapter 36 of Clayden, Greaves, and Warren's Organic Chemistry, the second edition. We're continuing our chapter-by-chapter summaries.
Right. And our mission today, to get to grips with participation, rearrangement, and fragmentation. These are three really key reaction types.
They really fill in some important gaps, moving beyond those basic ionic reactions you mentioned earlier.
We're going to try and simplify these concepts, but without losing the important details. We'll focus on why, the mechanistic reasoning.
Exactly. Looking at the key pathways, how functional groups transform, and definitely highlighting stereochemistry and retrosynthesis, which are always crucial.
And we're keeping it accessible, hopefully, for you, our upper-level undergraduate listeners. We don't want to oversimplify, but we do want clarity.
Okay, so let's start with the first big idea, neighboring group participation, NGP.
NGP. It almost sounds friendly, doesn't it? Like a
Yeah.
helpful neighbor.
Huh. It kind of is in a molecular sense. We're talking about a group that's next door to the reaction center, not right at it.
And this neighbor actually helps out with the reaction, usually a substitution.
Precisely. And the effect isn't small. It can dramatically speed things up. It's really quite astonishing.
How dramatic are we talking?
Well, take something like phenylthiomethyl chloride, PHSCH2Cl, reacting with water-soluble lysis. It goes about 600 times faster than, say, THOCH2Ts, which lacks that neighboring sulfur.
600 times faster, just because of the sulfur nearby.
Yep. Or think about a carbon-carbon double bond participating. That can accelerate a reaction by a factor of, get this, 10 to the power of 11.
Wow, that's
Really?
astronomical. 100 billion times faster.
Mind-boggling, isn't it? It's not just giving the reaction a little nudge, it's like strapping a rocket to it. The molecule is practically helping itself react.
Okay, so how does that work, this sort of molecular self-help? What's the actual mechanism behind that massive speed boost?
The absolute key is forming a temporary cyclic intermediate. Think about those electron-rich atoms like sulfur with its lone pairs, or maybe an oxygen and an ether.
Or even pi electrons, like in that double bond example.
Exactly. Those electrons can sort of reach over and give the leaving group a push, helping it leave. As they do that, they form a little ring, maybe 3-membered, 5-membered, sometimes 6. Ah, okay, so this internal attack forms a ring.
And that intramolecular step, forming the ring, is often much faster than waiting for some external nucleophile to bump into the molecule in just the right way. It stabilizes the whole process.
Makes sense. But forming rings involving neighboring groups, does this mess with the stereochemistry? That seems like a place things could get complicated.
Ah, now you're asking the really crucial question.
Yeah.
Because the stereochemistry is where NGP gets incredibly interesting. It's actually the strongest evidence for NGP happening.
How so? What happens differently?
Well, you know how a standard SN1 reaction often scrambles stereochemistry because you get that flat carbocation?
Right, race homonymization usually. And
Yeah.
SN2 famously gives inversion of it.
Exactly, but NGP often leads to overall retention of stereochemistry. The configuration at the reaction center ends up the same as it started.
Retention. But how? If the neighboring group attacks like an SN2, shouldn't that invert it? It does. That's the first step. The neighboring group attacks intermolecularly from the back, kicks out the leaving group that's inversion number 1, you get your cyclic intermediate.
Okay, so we're inverted at that point.
Right. Then the external nucleophile comes in. And how does it attack the cyclic intermediate?
Also from the back, like another SN2.
Precisely. It attacks the carbon from the side opposite the neighboring group bond, causing a second inversion.
So invert once, then invert again. Brings you back where you started, like a double flip.
Exactly like a molecular double backflip. You land facing the same direction. Overall retention of relative stereochemistry.
So if you see a substitution reaction happening at a chiral center, and the product has the same configuration as the starting material, That's a huge red flag for NGP.
It's your biggest clue. There's a classic example with R2-bromopropanoic acid. Treat it with strong base, like concentrated NaOH, and you get standard SN2 inversion, S-lactic acid.
Makes sense. Strong nucleophile, SN2.
If you use silver oxide, maybe with just a tiny bit of hydroxide,
Silver ions love halogens. They'll pull off the bromide.
they encourage the bromide to leave, making it more like an SN1 ionization initially. But before an external nucleophile can get there, the molecule's own carboxylate group swings around.
The COO- group. It attacks internally.
It attacks internally, forming a little three-membered ring intermediate called a lactone. That's NGP in action.
Yeah, there's inversion number 1.
Then the hydroxide, even at low concentration, attacks that lactone,
Second inversion.
giving you lactic acid, retention overall. It's beautiful evidence. And the key principle here is crucial. Neighboring groups only jump in if doing so actually makes the reaction faster.
Right, they won't participate if it's slower than the normal route.
Exactly. If NGP doesn't offer a speed advantage, the molecule just defaults to the standard SN1 or SN2 pathway, whatever's available. Nature takes the fastest path.
It's always seeking the path of least resistance, or I guess lowest activation energy.
Okay, so what kinds of groups can act as these helpful neighbors? We mentioned sulfur, oxygen, pi bonds. Those are big ones. Electron-rich heteroatoms are great participants. Sulfides, ethers, even amines, esters, carboxylates. Sulfides tend to be better than ethers, incidentally.
Why is that? Sulfur's bigger, more polarizable.
Exactly. Those bigger, softer orbitals are better at donating electron density. Distance matters too. And oxygen further down the chain might participate by forming, say, a 5-membered ring intermediate, which is also quite favorable.
So 3 and 5-membered rings are common.
3, 5, and sometimes 6 are the most common for NGP intermediates. 4-membered rings are usually 2-strained, and 7-membered are often entropically disfavored, too floppy to form easily.
We mentioned pi electrons from double bonds accelerating reactions massively. How does that work stereochemically? Do you still get retention?
You often get interesting stereochemical outcomes. The double bond can participate to form a sort of bridged, non-classical carbocation intermediate. It's often symmetrical.
Symmetrical, so if the nucleophile attacks, it could attack either side.
Right, which means even if you start with one enantiomer, you might end up with a racemic mixture, depending on where the nucleophile attacks that symmetrical intermediate. Phenyl groups can do this too.
A whole benzene ring participating.
Yep, forms a phenonium ion intermediate. Donald Cram did some beautiful work on this back in 1949. He showed you could get retention of relative stereochemistry between adjacent centers, but if the phenonium ion intermediate was a chiral, you'd lose the absolute stereochemistry and get a racemic product. It's subtle but powerful.
Okay, so NGP is this internal assistance, often leading to retention or sometimes specific scrambling via symmetrical intermediates. But sometimes this process goes even further.
It does. Sometimes that participating group doesn't just help out temporarily. It actually ends up migrating. It finishes the reaction attached to a different atom entirely.
And that takes us from participation into the realm of rearrangements, where the whole molecular skeleton can change.
Exactly. The line can be a bit blurry sometimes, but a rearrangement fundamentally involves breaking and making CC or C-heteroatom bonds in a way that changes the core connectivity of the molecule.
Can we see this happening? Like track where atoms move?
We can. Isotopic labeling is fantastic for this. Imagine a phenyl group participating, maybe migrating during a reaction. If you label one specific carbon in that phenyl ring with carbon-14.
The radioactive isotope.
Right. You can then see where that label ends up in the product. If the intermediate was symmetrical, like that phenonium ion, you might find the label scrambled, say, 50% on the original carbon and 50% on another position, proving the migration occurred through that symmetrical state.
Clever. What about other groups migrating, like nitrogen and amines?
Oh, yes, aнимine migrations happen. You can have, say, a chloramine, where the amine nitrogen acts as an internal nucleophile, displaces the chloride, forming a 3-membered ring called an aziridinium ion.
Like the NGP step.
Exactly. But then, when an external nucleophile like hydroxide comes in, it might attack the other carbon of that aziridinium ring.
Ah. So the nitrogen started on carbon-1, formed the ring with carbon-2, and the hydroxide attacks carbon-1, leaving the nitrogen now attached to carbon-2.
Precisely. The amine group effectively migrates from C1 to C2. This often happens if, say, C1 is less sterically hindered, making it the preferred site for the external nucleophile attack.
And there's specific named rearrangements based on this kind of migration too, right? Like the Payne rearrangement.
The pain rearrangement is a neat one involving epoxy alcohols and base. The alkoxide formed from the alcohol attacks the epoxide intramolecularly,
Opening the epoxide.
opening the original epoxide and forming a new epoxide further down the chain, with the alcohol now where the epoxide used to be. It's an equilibrium, shuffling the epoxide and alcohol positions.
Fascinating. So participation can lead directly to these skeletal changes. But what about rearrangements driven purely by, say, instability? Like forming a really unhappy carbocation?
That's the driving force behind perhaps the most famous class, the Wagner-Meerwein rearrangements involving alkyl group migrations. The classic scenario is trying to form a primary carbocation via SN1.
Which are notoriously unstable.
Extremely unstable. Take neopentyl iodide, that's CH3, 3CCH2I. If the iodide leaves, you'd expect a primary carbocation on that CH2.
But it's right next to that bulky tertiary carbon.
And nature avoids that primary carbon. Instead, as the iodide leaves, or just after, one of the methyl groups from the adjacent tertiary carbon essentially slides over to the primary carbon.
The whole CH3 group moves.
The whole methyl group, taking its bonding electrons with it. The electrons in that CC sigma bond basically overlap with the developing empty orbital on the primary carbon.
And what does that leave behind?
It leaves behind a positive charge on the carbon the methyl group just left, which is now a much, much more stable tertiary carbocation.
So the molecule rearranges itself instantly to avoid the unstable primary cation and form a stable tertiary one instead. That's the Wagner-Meerwein shift.
That's the essence of it. And these shifts are incredibly fast. We can actually observe carbocations using NMR spectroscopy at very low temperatures where they're stable enough.
Like see a secondary cation.
Yeah, you can sometimes see, say, the sec-butyl cation. But if you warm it up even slightly, boom, it instantly rearranges to the more stable tert-butyl cation. Hydrogen atoms can migrate too, not just alkyl groups. These are called hydride shifts.
So H- effectively jumps over.
Effectively, yes. The mechanism involves the sigma bonding electrons of the CH bond overlapping with the empty orbital, allowing the H to shift. It's all about orbital overlap with a filled sigma bond apero donating into the empty orbital LUMO.
And these shifts aren't just theoretical curiosities, right? They happen in real syntheses.
Oh, constantly. They have major consequences. Think about trying to dehydrate camphonol with acid. You protonate the alcohol, it leaves, you form a secondary carbocation.
Okay.
But eliminating a proton from there to form a double bond would require putting a double bond at a bridgehead carbon in that bicyclic system.
Which violates Bredett's rule. You can't do that in small, strained rings.
Exactly. The direct elimination pathway is blocked. So what happens instead?
A methyl group migrates, like Wagner-Meerwein.
Precisely. A methyl group shifts, relieving some strain and forming a different tertiary carbocation, which can then lose a proton without violating Brett's rule, giving you the product, xanthine. It's a classic example of rearrangement enabling a reaction.
That's really neat. It's like the molecule finds a detour. You mentioned numbering carbons is key for tracking these complex ones.
Absolutely essential, especially with bicyclic systems like isobornyl rearranging to camphene. If you don't carefully number every carbon in the starting material and track where each number goes during the proposed shifts, it's incredibly easy to get lost. That's my top tip. Number everything.
Good tip. Now, sometimes rearrangements don't just involve shifting groups, but expanding rings.
Yes, especially when driven by ring strain. Imagine a carbocation forming next to a strained four-membered wing.
Like cyclobutane. Lots of angle strain there.
A lot of strain. That ring wants to open up. So one of the CC bonds in the four-membered ring can migrate to the adjacent carbocation center.
Expanding the ring to 5 members.
Exactly. It expands to a less strained 5-membered ring, even if the new carbocation formed is, say, secondary instead of tertiary. The relief of ring strain is often a more powerful driving force than just forming the most substituted cation.
So strain relief can trump carbostability sometimes.
It definitely can. We see this used synthetically, like in making a caryophyllene alcohol, where expanding a 4-membered ring is a key step.
So these carbocation rearrangements, overall, are they helpful or a hindrance for synthetic chemists? A blessing or a curse?
That's the perfect way to put it, because they're genuinely both. They are a blessing when you can predict and control them to build complex structures that would be incredibly difficult otherwise. Think of some of those natural product syntheses.
But the curse part?
The curse is when they happen when you don't want them to. The classic example is Friedel-Crafts alkylation. You try to put a straight propyl group onto a benzene ring using propyl chloride and LCO3.
And you expect propylbenzene.
But you mostly get isopropyl benzene because the primary carbocation intermediate rapidly rearranges via a hydride shift to the more stable secondary carbocation before it alkylates the ring. It can be really frustrating.
So to make them useful, you need control.
Absolutely. There are sort of three guidelines for a synthetically useful rearrangement. One, the rearrangement itself needs to be fast and clean. Two, the rearranged carbocation needs to be significantly more stable or offer a unique reaction pathway. And three, you need a reliable way to trap that rearranged cation quickly before it does something else unpredictable.
Control the chaos. Got it.
Yeah.
Okay, let's transition to some specific, famous named rearrangements. These seem to really capture these principles. Maybe start with the Pinacol rearrangement.
Ah, the Pinacol rearrangement. A true classic. It takes a 142-diol two alcohol groups on adjacent carbons and under acidic conditions rearranges it into a ketone or aldehyde. The prototype is kinacol itself turning into pinacolone.
Pinacol is that tetramethyl 142-diol, right?
Yes, that's the one. So acid protonates one hydroxyl group, making it a good leaving group, water.
Okay, water leaves, forming a carbocation.
Exactly, a tertiary carbocation in the case of pinacol. Now, here comes the push-pull magic. The lone pair on the other oxygen atom starts to push its electrons in to form a double bond, a carbonyl group.
That's the push and the pull.
The pull is the migration of one of the alkyl groups, a methyl group in pinacol, from the carbon with the remaining hydroxyl group over to the carbocation carbon.
So the methyl group shifts over, and the oxygen forms a CO double bond simultaneously.
Pretty much. It's driven by the immense stability gained by forming that strong carbonyl group. The migrating group just slides over as the positive charge is neutralized by the oxygen's lone pair forming the pi bond.
And this isn't just for simple molecules like Pinacol.
Not at all. It's incredibly powerful for making complex structures, especially spirocyclic systems where two rings share just one carbon atom. You can set up a diol on a bicyclic framework, and the Pinacol rearrangement can stitch together a spirojunction very elegantly.
Cool. Are there related reactions, like with epoxides?
Yes. You can get Pinacol-like rearrangements from epoxides using Lewis acids, like magnesium bromide. Sometimes this leads to really surprising outcomes, especially if you then react it with something like a Grignard reagent. The Lewis acid opens the epoxide, maybe rearrangement happens, then the Grignard adds. You can get complex products.
And what if the diol isn't symmetrical? Does one group prefer to migrate over another?
Good question. Yes, there's regioselectivity. Generally, the hydroxyl group that leaves to form the initial carbocation is the one that forms the most stable carbocation.
So next to a phenyl ring, benzoylic, or a tertiary carbon, would be preferred over secondary or primary.
Exactly. And then when it comes to which group migrates, there's also a preference. Groups better able to stabilize positive charge tend to migrate more readily, like aryl groups or hydride over alkyl groups sometimes. It depends on the specific system.
Okay, so Pinacol is acid catalyzed. What if you want more control over which group migrates or which hydroxyl leaves?
That's where the semi-Pinacol rearrangement comes in. Here, instead of relying on acid to protonate one hydroxyl, you selectively convert one of them into a really good leaving group, often by making it a tosylate. OTs.
And you'd usually make the less hindered alcohol into the tosylate.
Often, yes, because it's easier to react selectively. Now, when that tosylate leaves, perhaps encouraged by mild conditions, the rearrangement is forced to happen in a specific way. The migration occurs anti-paraplanar to the departing tosylate group.
That anti-paraplanar requirement again, like E2 eliminations.
Exactly the same geometric requirement. This gives you fantastic control over the regiochemistry, which group migrates, and where the new carbonyl ends up. It's incredibly valuable in synthesis.
Any famous examples?
Oh, yeah. E.J. Corey used a semi-Pinacol strategy in his synthesis of longophyllene. It's also key in making bergamotine derivatives from 2-iodo alcohols. It's a reliable tool.
You can also trigger these via diazonium salts, right? The Tiffano-Demjanov reaction.
That's another important variant. You start with an amino alcohol. You treat it with nitrous acid, HONO, to form an alkyl diazonium salt, Rn2+.
And diazonium ions have N2 as a leaving group, which is an amazing leaving group.
One of the best. Nitrogen gas just bubbles away. As the N2 leaves, it generates a carbocation, and just like in the Pinacol semi-Pinacol, a group migrates from the adjacent carbon to trigger the rearrangement, usually forming a ketone or aldehyde, often with ring expansion if the starting material was cyclic.
Ring expansion, like adding a carbon to the ring.
Yes. The Tiffano-Demjanov is often used for one-carbon ring expansions of cyclic ketones via the intermediate amino alcohol. Related to this is reacting a ketone with diazomethane CH2 and 2.
Doesn't that just insert a CH2 group?
It can, leading to ring expansion. Diazomethane adds to the ketone, forms an intermediate that rearranges, kicks out N2, and inserts the CH2 group next to the carbonyl, expanding the ring by one carbon.
Wow, lots of ways to rearrange things. What about going the other way, like the dinone-phenol rearrangement? Sounds like it makes rings more stable.
It absolutely does. This one is sort of like a reverse pinnacle rearrangement in terms of complexity change, but the driving force is different. You start with a dienone, often a bicyclic one.
Two double bonds and a ketone.
Right, often in a cyclohexadiene system. Under acidic conditions, a group migrates, and the whole system rearranges to form a stable aromatic phenol ring.
Ah, the driving force is gaining aromaticity. That's huge thermodynamically.
Exactly. It's a very powerful driving force. This rearrangement was actually historically super important in the synthesis of steroid hormones, like oestrone. Carl Djurassi's work in this area was fundamental to the development of the contraceptive pill.
Incredible connection to medicine. Okay, another historical one. The benzylic acid rearrangement.
Yes, discovered way back in 1838 by Justus von Liebig, he found that benzyl, which is a Quenker-2 diketone, Ficoco, reacts with strong base like hydroxide.
What happens?
The hydroxide attacks one of the carbonyl carbons, forming a tetrahedral intermediate, just like standard nucleophilic addition.
Okay.
But then, instead of just getting protonated, the adjacent phenyl group migrates from the other carbonyl carbon over to the one the hydroxide just attacked. This happens as the negative charge on the oxygen kicks back down.
Kind of like the pinnacle push-pull, but starting from a diketone and driven by a hydroxide attack.
Very similar idea, yes. It collapses to form the carboxylate of benzylic acid, which is dihydroxydiphenylacetic acid, PH2COH. A phenyl group migrates.
Neat. Now, one that always seemed a bit weird is the Favorsky rearrangement, that hairpin bend mechanism.
Ah, the Favorsky. It is a surprising one. You take a ketone with a halogen on the carbon next to the carbonyl.
Okay, like 2-chlorocyclohexanone.
Perfect example. You treat it with a base, typically an alkoxide like sodium phthioxide, NaOET, and you don't get simple substitution. Instead, you get an ester, often with ring contraction.
Ring contraction. So 2-chlorocyclohexanone gives a cyclopentane derivative.
Exactly. You end up with ethyl cyclopentane carboxylate. The 6-membered ring shrinks to a 5-membered ring with an ester group attached.
How on earth does that happen? It's not like the benzylic acid thing.
That was the initial thought, something analogous. But the real mechanism, for most cases, is much cooler. The alkoxide acts as a base first, not a nucleophile. It pulls off a proton from the other side of the ketone, the OS position.
Forming an enolate.
Right. And that enolate then does an intramolecular SN2 reaction, attacking the carbon that has the halogen atom attached.
Wait, the enolate attacks the carbon with the halogen from the same molecule. What does that form?
It forms a highly strained 3-membered ring fused to the original ring, a cyclopropanone intermediate.
A cyclopropanone. Wow, those must be reactive.
Extremely. The alkoxide, which we still have plenty of, then attacks the carbonyl carbon of this strained cyclopropanone.
Okay, opens the tetrahedral intermediate.
And when that tetrahedral intermediate collapses, it doesn't reform the cyclopropanone. Instead, the most strained bond of the 3-membered ring breaks, often the bond that was part of the original ring, leading to the ring contraction. The electrons flow, you eventually get protonated, and bam, ring contracted ester.
That is a hairpin bend. Enolate formation, intramolecular SN2 to make a cyclopropanone, nucleophilic attack, and ring opening contraction. Wild.
It's a fantastic mechanism. It was used in the synthesis of cubane, that amazing caged hydrocarbon. Although sometimes, if there are no I protons to remove, a benzylic acid-type Favorsky can happen, like in the synthesis of the painkiller pethidine.
Versatile. Okay, last big rearrangement type, migration to oxygen, the Baeyer-Villiger reaction.
Ah, the Baeyer-Villiger oxidation, another incredibly useful one. Here, you treat a ketone or sometimes an aldehyde with a peroxy acid like MCPCA.
Peroxy acids have that extra oxygen, OOH.
Exactly. And the net result is that an oxygen atom gets inserted into a CC bond right next to the original cardinal group. So a ketone becomes an ester. Or a cyclic ketone becomes a lactone, a cyclic ester.
Molecular surgery, inserting an oxygen atom. How does the mechanism work?
The peroxy acid adds to the carbonyl carbon first, forming a tetrahedral intermediate, sometimes called the Kriege intermediate.
Similar to hemiacetal formation.
Sort of, but with the peroxy group. Then comes the key step. It rearranges. The bond between the oxygens and the peroxy part breaks, the carboxylate part leaves, and simultaneously, one of the alkyl or aryl groups attached to the original carbonyl carbon migrates over to the oxygen atom that remains attached.
The group moves from carbon onto the oxygen.
Precisely. It's pushed by the lone pair on the oxygen it leaves behind, which becomes the new ester-lactone oxygen, and pulled by the departing carboxylate. It's a concerted migration and loss of the leaving group.
Okay, crucial question. Which group migrates if the ketone is unsymmetrical? Say methylphenyl ketone. Does the methyl move or the phenyl move?
There's a very clear migratory aptitude, a preference order, and it's generally tertiary alkyl groups migrate best, then secondary alkyl and phenyl groups are roughly similar, then primary alkyl like ethyl, and finally methyl migrates least readily.
So tertiary, secondary, phenyl, primary methyl.
That's the order. It correlates pretty well with the ability of the migrating group to stabilize a developing positive charge in the transition state of the migration step. Phenyl groups and more substituted alkyl groups are better at this.
That makes it really predictable and useful synthetically then.
Hugely useful. For example, it was used in a synthesis of L-DuP, a Parkinson's drug, from L-tyrosine, selectively inserting an oxygen to make the desired catechol structure.
And what about the stereochemistry of the migrating group? If you have a chiral group moving, does it keep its configuration?
Yes. Just like in many other 1-Ver2 migrations we've discussed, the Bayer-Villiger migration proceeds with complete retention of stereochemistry at the migrating center. This p3 orbital just sort of smoothly transfers its overlap from the carbon to the oxygen without any inversion. It's a fundamental aspect of these concerted 1-Borger2 shifts.
Retention again. That seems to be a recurring theme when bonds shift around like this.
Yeah.
Okay, that covers a lot of ground on rearrangement. Let's switch gears finally to fragmentation reactions, breaking the skeleton apart.
Right. So rearrangements change the connectivity, but often keep the same number of atoms. Fragmentations actually break CC single bonds, splitting the molecule into usually 3 distinct pieces.
3 pieces. What drives this kind of cleavage?
It always requires both an electron push and an electron pull, positioned correctly across the CC bond you want to break. You need an electron source, often a lone pair, on an oxygen or nitrogen position to push electrons towards the bond.
That's the push.
And you need an electron sink, usually a leaving group or a developing carbocation, positioned on the other side of the bond to pull electron density away from it.
The pull, so push and pull across the CC bond, weakens it enough to break.
Exactly. It polarizes that CC bond, making it the weak link that snaps. The molecule essentially falls apart into 3 fragments: the electron source piece, the connecting piece containing the broken CC bond, often becoming a double bond, and the electron sink piece, the leaving group or incommutation.
Can you give an example?
Sure. Imagine a cyclic 1003 diol. If you protonate one alcohol, the sink-leaving group, the lone pair on the other oxygen, the source, can push electrons through the CC bond, connecting them, breaking it.
And what would the pieces be?
You'd get water from the leaving group, a protonated carbonyl from the oxygen that pushed, and an alkene fragment from the carbon chain in between. Ring strain relief can be a big driving force here, too.
So like rearrangements, stereochemistry must be important here, too. That push and pull need to be aligned.
Critically important. Just like E2 eliminations and some semi-pentacle rearrangements, fragmentation generally requires the electron source, the breaking CC bond, and the electron sink-leaving group to be anti-paraplanar, all lined up in a plane, but alternating sides.
That specific zigzag alignment.
Yes. If the molecule can't adopt a conformation where that alignment is possible, fragmentation won't happen or it'll be very slow. Instead, you might get elimination or substitution. This conformational requirement gives chemists amazing control.
How so?
Well, consider cis and transducalin derivatives with appropriate functional groups. One isomer might have the perfect anti-paraplanar setup for fragmentation, while the other isomer, because of its fixed chair conformation, might only be able to undergo elimination. Conformation dictates reactivity.
This sounds like it could be really useful for making otherwise difficult structures,
Right.
like those medium-sized rings, 8, 9, 10 members.
Exactly. Medium rings are notoriously hard to make by direct cyclization due to entropy and transannular strain. But fragmentation offers a clever workaround. You can build a fused bicyclic system, like a decalin, 2 fused 6-membered rings.
Okay. Relatively easy to make.
And then set it up so that a bond connecting the 2 rings is anti-paraplanar to a leaving group on one side and an electron donating group on the other. Trigger the fragmentation and that connecting bond breaks. effectively unzipping the fuse system into one large single 10-membered ring.
Wow, that's elegant. Building small rings, then breaking one bond to make a big one.
It's a fantastic strategy, and because of that strict stereochemical requirement, you can often control the geometry, cis or trans, of the double bond formed in the resulting medium ring with high precision. Corey used this beautifully in his synthesis of caryophyllene.
Are there named fragmentation reactions too?
There are variations. For example, the Beckmann rearrangement of oximes normally forms amides. But if the group that would migrate is tertiary and therefore capable of forming a stable tertiary carbocation.
It might just leave as a cation instead of migrating.
Exactly. Instead of migrating, it can act as the pull, or electron sink. The CC bond next to it breaks, pushed by the nitrogen lone pair, and the molecule fragments into a stable tertiary carbocation and a nitrile C triple bond N.
So the Beckmann can become a fragmentation if you have a suitable tertiary group, like in camphor oxime.
Camphor oxime is a classic example where fragmentation occurs instead of the expected Beckmann rearrangement. Again, it's about that push-pull across the CC bond, facilitated by the stability of the departing group.
And the Eschen-Moser fragmentation. That sounds specific.
The Eschen-Moser fragmentation is a really important method specifically for making keto-alkanes molecules with both a ketone and a CC triple bond separated by some carbons.
How did that work?
You typically start with an apopoxy ketone, you convert it to a tosyl hydrazone derivative, then, under basic conditions, a beautifully concerted fragmentation cascade happens.
Inserted all at once.
Essentially, the base initiates things, lightly deprotonating. Electrons shuffle around. The epoxide ring opens, providing the push from the newly formed alkoxide. The CC bond next to the original ketone fragments. The CN double bond shifts, and you eliminate nitrogen gas, N2, and the tosyl group, TS, forming the alkyne.
Wow, a lot happens, but driven by that N2 leaving group again.
The loss of stable N2 and Ts provides a huge thermodynamic pull. And critically, all the bonds involved in breaking and forming align antiparaplanar in the transition state for this smooth cascade to occur. It's stereoelectronically controlled.
Amazing. So fragmentation lets you make medium rings, control double bonds, even make alkynes. Let's wrap up with that Nootkatone story you mentioned earlier. It really showcases fragmentation, right?
It really does. Nootkatone is this bicyclic ketone with a distinct grapefruit aroma. For a long time, everyone thought it was the main flavor component of grapefruit.
So chemists wanted to synthesize it.
Naturally. It became a popular target in the 70s. And what's fascinating is that several different successful syntheses relied heavily on fragmentation reactions as key steps. Different groups came up with ingenious ways to build precursors containing 3, 4, or 6-membered rings designed to fragment open.
In just the right way to form the complex bicyclic skeleton of Nootkatone.
Exactly. They use the principles we've discussed, setting up the push-pull, ensuring the antiparaplanar alignment to break CC bonds strategically and construct this intricate natural product. Really clever chemistry.
So they made it. Did it taste like grapefruit? Did they solve the flavor mystery?
They made it beautifully. Several elegant syntheses. But here's the twist in the tale.
Oh.
It turns out Nootkatone, while definitely present and aromatic, isn't the primary impact compound for that super sharp characteristic grapefruit flavor and smell.
It's not. After all that work, what is it then?
The real culprit, responsible for that intense note, is actually a thiol, a sulfur-containing compound present in incredibly tiny parts per trillion concentrations, something humans are exquisitely sensitive to.
Wow. So the syntheses were amazing chemistry, but based on a slightly wrong premise about the flavor itself.
Pretty much. But far from being a waste, those syntheses were triumphs of chemical strategy. They developed and showcased powerful fragmentation methods and, in the process, helped correct a long-standing misconception in flavor science. It's a great story about how synthesis can probe biological questions.
That's a fantastic example.
Sure.
Okay, so let's try and bring this all together. We've covered a lot of ground today.
We really have. We've dived deep into how molecules do these incredible things: participation, rearrangement, fragmentation, changing their skeletons, breaking apart.
But always following underlying rules, driven by electronics, stability, and especially stereochemistry. That antiparaplanar requirement pops up again and again.
It really does. It highlights how 3D shape dictates reactivity. We've seen how subtle factors control entire pathways, letting chemists build seriously complex molecules with surprising precision.
And hopefully for you listening, seeing these mechanisms isn't just about memorizing named reactions. It's about grasping the logic, right? Seeing how molecules transform based on these fundamental principles.
Exactly. It's like understanding the grammar of molecular transformations. These aren't just abstract concepts, they're at the heart of making medicines, materials, fragrances, flavors, everything around us.
So the next time you see a reaction in your textbook or research paper that looks, well, a bit weird, or seems to take an impossible route,
Maybe pause and think. Could there be a neighboring group helping out? Is the molecule rearranging to find stability or relieve strain? Is there a hidden push and pull setting up a fragmentation?
what other molecular puzzles could be solved by looking for these patterns? It really is like molecular problem solving, isn't it? Thinking about how these reactions work is almost like figuring out nature's own elegant solutions.
Beautifully put. And on that note, thank you for joining us on this deep dive into Chapter 36 of Clayden, Greaves, and Warren.
And thank you for being part of the Last Minute Lecture family. We hope this exploration helps you connect the dots in your understanding of organic chemistry.